Namaste and welcome to the channel. So I hope the topic of discussion is already clear with the title. We'll be talking about GNSS. Satellite-based navigation systems are often used in smartphones, car navigation systems, your smartwatch, and many other things obviously. So let us know in the comment section what you guys are using satellite navigation for. Before we go any further, I would like to point out something. Have you ever noticed that sometimes brand becomes so much popular that the product or service they provide is synonymous with that brand, to such an extent that both of their names are interchangeably used? For example, photocopy and Xerox. Xerox was the brand that developed the first photocopy machine. But nowadays, photocopy and Xerox are used interchangeably and hardly anyone says photocopy. It's always Xerox. Take for instance Maggi as well. Maggi is a brand of noodles, but it is often related to noodles. Whenever you say noodles, the first thing that pops up is Maggi. Same for a soft drink. It's always Coca-Cola, isn't it? Similarly, that has happened for GNSS or Global Navigation Satellite-based Systems. So GPS is a subset of GNSS, but it has become so popular that often the terms are interchangeably used. So the satellites are revolving around Earth in a dedicated orbit. You have geosynchronous orbits, medium Earth orbits, low Earth orbits. Basically, the altitude of the satellites differ according to the orbit they have selected. So LEO, or the low Earth orbit, is where our International Space Station is. I hope you've heard about that. Then we have medium Earth orbit, in which most of the satellites for satellite navigation is present. For instance, GPS, Galileo, then GLONASS, Baidu. Geosynchronous orbit is the one in which India's NAVIC, GAGAN, and all of that satellites are. So basically, with the altitude, the revolving speed is also different, because the closer you are to Earth, the more is the gravitational pull and the more centrifugal force you require to stay in that particular orbit. So I think in low Earth orbit, the space station is revolving around Earth in about 90 minutes. Only 90 minutes, that's right. And in the medium Earth orbit, GPS satellites are revolving around Earth in around close to 12 hours. And the geosynchronous orbit satellites are revolving around Earth in 24 hours. So that's equal to 1 day in our time period, right? So our satellite orbit is in the shape of an ellipse, and Earth is sitting at one of its focus. The closest distance between Earth and the satellite orbit is known as perigee, and the farthest distance is known as apogee. These are just, jargons used in GPS based or GNSS based stuffs. Then there is angle of inclination, which is the angle between the satellite's orbital plane and the equatorial orbital plane. There is ephemeris and almanac. So ephemeris is the orbital data of your particular satellite, while almanac is the rough approximate of orbital data of all the other satellites surrounding you. We also have an example of almanac of satellite with PRN01. You can see that it has the ID, health, eccentricity, and all that typical data associated with a satellite. Next up, elevation. Basically, elevation is the angle between your horizontal plane of location that you are currently situated at and the satellite's line of sight direction. So basically, this gives you an approximation of where your satellite is. If the angle is 0 degree, that means the satellite is at the horizon. If it's 90 degree, that means your satellite is right above your head. You want it to be visible to your receiver, so a 0 degree is not good enough for the receiver. Azimuth is the horizontal angle between the satellite and the true north. So basically, it is a clockwise based angle. That's why 0 degree for north, 90 degree for east, 180 for south, 270 for west, and again 360 or 0 degree for north. So combining azimuth and elevation, what you can get is the correct position of your satellite in space. There are quite a number of bands associated with satellites, depending upon the frequency that is being used by them. We have L band, S band, C band, and other bands as well. So mostly L band and S band are the most popular ones, and within L band we'll be going with L1 subband, which will have a frequency of around 1570 megahertz. That is what is supported by our u-blox chip that we'll be using. So in short, our whole GNSS system comprises of three main elements: space segment, user segment, and ground control segment. So space segment is obviously comprising of all the satellites, constellation. Then we have the user segment, that will be us, normal users, and defense users. So basically we receive the data from the satellites based on the particular frequency that our receiver is capable of listening to. And then we have the ground station, which is responsible for updating the satellites with the corrections involved, and also it receives data from the satellite. Based on that only the corrections can be provided, right? Here is a list of all the bands of frequency associated with different satellite constellation. You can observe that Galileo and Baidu have quite a number of bands of frequency close to each other. Obviously, the naming convention is different for such bands. We can also observe that GPS, GLONASS, and QZSS, these constellations have L1CA band, which will ultimately be used by our u-blox receiver. Galileo also has the even band with the same center frequency as L1CA band, but the type of modulation used is different. So even though the same set of antennas and RF front end can also receive even based signal, but the type of demodulation or decoding required would be different. GPS satellite constellation is at an altitude of around 20,000 km, and it has 6 orbital planes as compared to 3 to GLONASS. And as we have already talked, that it takes around 12 hours for a particular satellite to revolve around Earth. The beauty about the placement of satellites in GPS constellation is such that at any given point on Earth, at least 4 satellites are always pointing towards you. Look at how weak the GPS signal is. Roughly the power is around minus 130 dBm in this case. Obviously there are so many losses involved due to polarization mismatch, signal attenuation in space, and ionosphere. Here the gain of the reception antenna is plus 3 dB, and after all that losses and this gain, eventually the power available at the receiver input is minus 130 dBm. Obviously if you change the gain of your antenna, this could be slightly better. The satellite is continuously updating data at 50 bits per second of rate. The data is having ephemeris, almanac datas, health, and certain kind of timing related data. So basically, as every human being has a unique signature that he or she puts on a check or a legal document, similar to that, every satellite also have their unique signature, and we know them as PRN or pseudo random noise. Pseudo because it appears to be noise, but it's not. In a simplified block diagram, you can see that the data of the satellite, which is updated at 50 bits per second, is XORed, bitwise XORed with the CA code. And together this is then modulated over the L1 carrier frequency. So this technique is basically BPSK. Even more modern modulation techniques are used, but we won't be discussing that right now. So BPSK here indicates us that we have a digital data and an analog carrier, right? We'll talk about CA code and P code. So CA code is something that is used by the civilians, while P code is something that is used by military personnel. But what exactly is the difference? Understand them both as a unique ID. So CA code is also a unique sequence of bits that repeats itself, and they both are part of PRN sequences. So CA code basically is a repetition of 1024 bits after every millisecond. So this is what is used in our normal civilian based GPS receivers. But in case of P code, the code is so long that it repeats after approx 37 to 38 weeks. Yes, I know, it's pretty long time. So both of these codes are generated from the satellite's ID, and both of them are unique. So if this P data is so long, how is the receiver understanding like which satellite is sending the data? What they have done is they have allocated a specific week of data to a particular satellite. Let's say in this given week, satellite 1 will be sending the code of week 1, satellite 2 would be sending the code of week 2, and like that. And you don't need the whole week data for the receiver to understand which satellite it is referring to. Obviously, because of correlation and because these P codes are unique in their nature, even a small fraction of code received from the satellite can help the receiver to decode that which particular satellite is sending this data. Also, there is a TOW or time of week in the GPS data frame that helps to understand this particular receiver, which time of week it is. You can easily relate to that particular satellite. GLONASS is the Russian Federation's satellite constellation, and it basically has 3 orbital levels as compared to 6 of GPS, and the altitude is somewhere close to 20,000 kilometers. Galileo is the space constellation of European agency, and the biggest reason for this kind of constellations to be working is they want independence from GPS. And that was the same reason why China, India started with their space constellations. So one extremely helpful use case of Galileo is search and rescue service. So how is position exactly calculated? To correctly calculate your position, you need at least 4 GPS satellites. As we have already discussed how the position of satellites are exactly kept in the constellation. So basically you need at least 4 separate satellites to calculate 4 unknown variables, that is user's longitude, latitude, altitude, and the time. In real conditions, it is always such that at first the range that is calculated by us or the exact precise location calculated by the receiver is not correct and differs from the actual location details. Why this happens? Because the time synchronization has not taken place between the receiver's clock and GPS clock. So basically GPS has atomic clocks and they are precise up to a certain extent. Obviously they also drift over time, but still they are much precise than what we have on a receiver. So both of the time is different. Our receiver time on Earth is different and GPS time is different. So this difference in time causes the range to be different. Why? Because distance equal to speed into time, and speed is our speed in vacuum or air. So if the time calculated is wrong, your distance will always be wrong. That's why this delta t, the time difference between satellite and our GPS receiver, is tried to be reduced. And as more and more satellites are tracked, then according to some mathematical analysis, the receiver tries to reduce the timing gap and synchronizes with the actual GPS time. Quite a number of errors can take place with your GPS measurements. As I already said, atomic clocks also tend to drift over time. That can also cause positioning error. Then satellite orbital data. Multipath is also a crucial thing that happens when your GPS signals are reflected through trees, buildings, etc. There is a term DOPE often used in GPS based systems, that is dilution of precision. So DOP basically gives you an idea of how exactly your satellite configuration is right now. You have GDOP, PDOP, HDOP, VDOP, various terms, but mostly PDOP, HDOP, and VDOP are used. Assume that your satellite is the center of a circle and the calculated distance from your satellite to receiver is one of the radius and the other radius is the actual distance between your satellite and the GPS receiver. So let's say if the two satellites are farther to each other, then this circle will be coinciding at a particular point, and at that point the area of intersection will have much larger angle. Then that means the DOP value is low, while if the area of intersection would be flatter and the angle would be lesser, that means the DOP value is high. In case of volume, you can see that if the volume covered by all of your satellites combined a 3D volume. If that's larger, that means your DOP is low. While if your volume covered is smaller, that means your DOP is high. Now let's explore the term DGPS, which is differential GPS. It helps in assuring a more precise positional data for your user. Basically, you can have a local DGPS. There is a reference station of GPS reference station that updates you with the positional information of all the satellites. Thereby you can improve it, and ultimately your position can be accurate or more precise. We'll be talking about SBAS, or satellite based augmentation systems. So there are two standards, RTCA and RTCM. These standards are nothing but a type of standards that in which data is transmitted. So let's not go into detail about that. You just have a look that GPS satellite will give you an initial data, while SBAS satellites will help you correct that data and make it more precise. So SBAS based satellites transmit data in such a format that you do not require any additional hardware to decode that. So that is one plus point in having SBAS based satellites. So WAAS is the satellite constellation that covers American region. These satellites are mostly in the geosynchronous orbits, and so WAAS covers all of the North America, that is Canada, USA and Mexico. Then we have EGNOS for the European Union. Basically it covers part of Europe and I think Africa. Then we have MSAS, which is the SBAS for Japan. Also, there is GAGAN in India and Baidu in China. Alright, I'd like to have a special mention for GAGAN and NAVIC. So GAGAN is basically GPS aided geo augmented navigation. That's what it stands for. And this is what has been developed by Indian Space Research Organization, or ISRO. And right now we have two master control stations that is situated at Bangalore and Delhi respectively. Other than that, we have 3 satellites. 2 of them are working right now and 1 is at spare. So the 2 of them are PRN-127 and PRN-128. So these satellites are right now in the geosynchronous orbit. In NAVIC, we have around 7 satellites. 3 of them are in the geostationary orbit, while 4 of them are in inclined geosynchronous orbits. So NAVIC is an alternative for GPS in India and surrounding regions. Obviously, GPS supports global range, while Indian Space Research Organization wanted NAVIC to be an RNSS, or regional navigation based satellite system. So right now NAVIC supports L5 and S band. I think they are already working on how to support L1 band as well. Alright, so the chip that we'll be using is u-blox Neo 6M. Yes, this module was lying around and I thought just to give it a try. Obviously you should not use this chip in your new product design because it has reached its EOL, or end of life. So you should go on with the recommended new chips. We'll be discussing the datasheet. The reason that I was talking about so many terminologies and concepts with revolving around GPS was so that we can easily read the datasheet and it doesn't take much time for us to understand what each term means. So in the datasheet, you can easily see that u-blox chip has 2 million correlators. Just imagine how fast all that mathematical process would be happening behind the scene, wherein I create a certain PRN value and then I relate it to the data that I've received. Oh, it's not matching. Let's change the phase. It's not matching. Let's move to another PRN with CA code. This is how it is happening behind the scene. I mean, it's truly amazing. This chip has around 50 channels. So each channel can be understood as something which is receiving data for every satellite and for every frequency. So if a satellite is, our receiver is not supporting anything beyond L1 CA, and that too only in GPS constellation, as you can see. But if this chip was supporting L1, L2, L5, then the satellite which is transmitting at all of this frequency needs at least 3 channels. One for L1, one for L2, one for L5. So each channel for every satellite and for every frequency. That is how the channels are distributed. SBAS satellites also will be taking your channels, so keep that in mind as well. So next is SBAS. We have already discussed. This chip supports WAAS, EGNOS, and MSAS. Of course, we are in India, and all of these three constellations are not in our region, but we have GAGAN here. So we'll be looking into GAGAN's geosynchronous satellites later on in the next coming up series. Then we have time to first fix, and obviously if your chip is just powered on, it will take more time as compared to when it is in shutdown mode or some other power sleeping mode. Like we have already discussed, minus 130 dBm was the GPS signal power that we were receiving, but keep in mind that was for plus 3 dB antenna gain. If you have more, then your obviously the signal power at your input side of the chip would be more. So here the sensitivity for cold start is the maximum one, wherein your recommended signal strength should be more than minus 147 dBm. Other than that, obviously you can see the position accuracy when you're using only GPS satellites and when you're using SBAS. Then we have time pulse. We haven't discussed about that, but understand it as something like the GPS is creating a timing sequence of its own, like 1 pulse per second. And this here is the accuracy for that time sequence that it is creating. Then you have velocity accuracy, heading accuracy, and all that stuff. The block diagram of this chip is also provided. You can have a look at the RF front end, which also has an LNA, low noise amplifier. Then we have the antenna, and then we have simple RTCs, GPS engine, and all that stuffs, digital filters. Rest in the boot time configuration, we already will be having the default sequence, that is a 9600 baud rate, and the protocol selected is NMEA, with all these messages being displayed: GSV, RMC, GSA, GGA, GLL, VTG, and TXT. But we will be interested in only two of these messages, that is GGA and GSV. Rest all you can have a look if you are interested, but I won't be talking about any other. And even in the code sequence, we'll be just be decoding these two messages. That would be it in this video. In the upcoming videos, we'll be discussing about the schematic of our development kit that we'll be using. We'll be covering programming for receiving and decoding the GPS data. And then finally, we'll be displaying the data on our TFT display of our development kit.
अब की बार
चैनल को लाइक, शेयर और सब्सक्राइब करो यार।
तो करो ना भाई, क्यों नहीं कर रहे?